So let's remember where we are. We were trying to understand how this car works, the computer, right? And what did we do? Like, let's have a real. We talked about. Make this okay. We talked about bits. Okay, how we can use bits to store information, and we said that bits by themselves doesn't matter, and bits need some kind of a context which will tell us whether how to interpret this. And we looked at how to operate on bits, operators, bitwise operators. Okay, and I suggest that please read the book. There's a lot that you need to learn in order to get ready for the exam, because in the lectures I'm focusing on the general big picture, but if you go back to the book, you will see that there are many examples where you will feel that, well, you need to learn a little bit more. Okay, and I suggest that you go over all the exercises within the chapter, and plus there are also some extra questions at the end. So please go over them, and I guarantee you that some of them will pop up in the exam. So please study the exercises in the book. After that, we started to covering how we represent numerical information, and for this, we studied, ints and unsigned numbers, of course, along with them, their representation, plus the operators, and then we then looked at, why this matters for as a programmers. So we looked at our programmer's perspective. We studied floats, and again, we looked at their representation, and then how we do plus and minus operators, and also, what it means for our programmer. So once we've done this, now we will move on to the other side. Remember, when we looked at these bits, it's not only the, ints, unsigned, and floats, but there are a lot of other things. Like, first, well, the program. Okay, how do we represent the program? Now, you've learned how to do programming, but you have little idea of basically what matters underneath. So in this case, we'll be focusing on machine level programming. Let's have a look at this. Now, before we study this, let's say that we will have a look at on Intel processors and architectures. We'll do this because Intel is the dominant CPU maker on at least the desktop machines, and within this course we'll be studying the Intel's architecture. Now there are other architectures like ARM, and Apple has the M1 architecture, like the M1 processor, and but once you know the basics of x86, which is actually a fairly difficult architecture, I believe that understanding the other architectures will be easy if you need to. Intel has a line of processors which we call x86. Okay, I'll tell you. And it's because Intel in 1978, they basically the first processor that they produced was 8086. Then they moved on, they produced other processors like 8286, 8386, and so on. But this 86 meant that all the processors were backward compatible. And what we mean by this is, if you have an executable here, remember in 8086, in this original processor, which was a very teeny tiny processor, they were able to support only a handful of instructions. But these instructions, and when they moved on to 286, for example, then they said, okay, let's have more instructions, more powerful instructions, but they still included them in 8086. If you had an executable dating back to 8086, and if you put this, for example, to the latest processor, say i9, if you give me this executable, this binary, it will still execute fine on your newest processor. This is called backwards compatibility, and this is one of the strategic decisions that Intel has made. Okay, and now this has a positive thing and a negative thing. Let me talk about, like how the design works. Basically, it's more like this. Okay, let's say that, if we have, you're building a house, but you have very little money. What do? You build a small, say, one-room house with some basic things, okay? And later you get more money. Okay, so let's say that this is my R8086. This is the set of instructions and registers that it supports. Then you get more money. In Intel's case, this means that they have access to more transistors, okay, so that they can build more complex systems. And then they build, like some extra instructions. Let's call this some extra thing. And let's say this was in 286, okay? Then they get more money, and like in the next year, then they devise another thing here. So these are just the extra add-ons. So when you talk about 386 supports all these instructions. And when you, for example, talk about, say that, I9, then you will have, like, this is, much complex, say, structure, but at its center here, the 8086 is still there. Now, this backward compatible is both nice because, like, it means for customers that, if you have an executable, anything that's designed for 8086, it's still, whatever the processor that comes up with from Intel, it will still be supported as a binary. Okay, that's the big thing. The downside is you can see that, like, you never start from a, clean slate. That means you don't have a clean design. It's always add-on. It's like, imagine a house that's built from, say, you have first a studio, then you build a second bedroom, a third room, and then, two more toilets, and etc. But you will still have that small studio at the center of your house. Okay, it will not be feasible. It's not a clean design. Okay, so that's the downside of Intel's processor. Now you will see that, like, there are other trends in processor design. Okay, ARM is one example where they started with a clean slate, and they have a much easier, much uniform design. And then it was actually advantages from a hardware point of and then with low power and etc. But this was Intel's decision, and in the end we have this clunky basically x86 architecture. Intel's approach was called CISC approach, which is complex instruction set compute, and this was basically a byproduct of the evolutionary design, meaning that there were many different instructions with many different formats. Okay, and note that for a lot of these formats, only for example a small subset is, for example, used with Linux programs. And this is a case, like, remember in our case that we have this and then this build and here, okay? And you can see that the instructions that we have here are more complex than the ones here, okay? And the format is also different, okay? But that's why we call this complex instruction set computer, or CISC approach. And then there is an alternative, like a school, which is called reduced instruction set computer, which is called RISC, okay? And an example for this is the ARM processors that we have. In this case, these guys didn't start like Intel from base, okay? And they started from scratch, and they made a design that is much simpler, okay? And that has a much reduced, that's like in this case, in this reduced instruction set computer, every instruction will do one thing in a clean way. And this is, so it has fewer instructions, it is a much easier syntax, and it's also easier to implement them in hardware, okay? And that's why, for example, ARM is available on mobile devices. That's why ARM dominated mobile devices than Intel, because Intel's architectures and processor were always too complex, okay? But despite, so there was quite a big fight between them, but despite this, clean design thing, Intel, in terms of speed, okay, at least, okay, was able to tune up their CISC processor, x86 processors, to match up and to compete with RISC computers. So this is kind of small evolution of Intel's x86. This, x86 was the first 16-bit Intel processors. Okay, and this is 16-bit means that every time you read from something from the memory, you get the 16-bit information. Okay, and this basically formed the basis for the first PC, which was designed by IBM, and also DOS, MS-DOS. And in this case, it dates back to 1978 with only 29,000 transistors running at 5 to 10 megahertz. And it had 1 megabyte memory, physical memory. And then came 386, which was a 32-bit instruction processor, the first one. It's referred to IA32, which is referred to as Intel architecture. And 85, like 10 times more processors running, 16 to 33. And this was the first one that would support Unix operating system, okay? And it added this flat addressing. And then came, 486, okay? And then after that, there come the time where Intel, instead of going with 586, they called it Pentium, okay? Pentium relates with 5. It's because they were competing with other processors, and they would produce, for example, when they were producing this 386, another processor would say, I have a processor that's called K386, okay? And a new processor that's a K486, it was easy to link for the other processors versus manufacturers to label their processors in line with Intel's. And Intel realized that it could not copyright numbers, okay? So that's why they switched to Pentium here instead of, and after that they never used this numbering in here. And this Pentium was the first 64-bit Intel processor, okay, which was referred to x86 64, and this is the one that you'll be using in this lecture. So this came in 2004, 125 billion, and 2.8 to 3.8 gigahertz. Okay, and then came Core 2, which is the first multi-core processor, and then i7, and then i9. I think it says now 8 or 16 cores, and the transistor is unknown, but some guess that it is more than 2 billion. Okay, and it's also running at a higher clock rate. So when we look at here, this is I think this is the Core 2, I think. Okay, no, it's probably like i7. So we have these 4 cores. Okay, identical cores. There's a cache which you'll learn here. Okay, and you could see that there were a lot of other things, there were specific instructions to add multimedia operations. They added some extra instructions to do more efficient conditional operations. They transitioned from 32 to 64 bits, and etc. These were the main things. And this was the i7's architecture, just to give you an idea, and you will be understanding what some of these things are, these cores, okay? And let me just see here. So, and this is also the latest i9 Alder Lake architecture. And one of the key things here is it has 2 different cores. Not all the cores are the same. They're called P cores and E cores. And P cores were optimized for performance, whereas E cores were optimized for efficiency, so that it could run different processors on different cores to make sure that it's not power hungry, or if it's something, if you need performance, that it would consume more powerful, but less efficient in terms of energy. And AMD is still around. Before there were a couple more processors, but AMD, and which is called Advanced Micro Devices. Well, it has it's just followed behind Intel, a little bit slow, but a lot cheaper. Okay, and when it founded, it recruited top circuit designers from the then there was this DEC. This was one of the mainframe computer systems, and they then basically put them together, and they built what's called Opteron, which was a competitor for Pentium 4, and then they developed x86 64, okay, and with their own extension to 64 bits. And this was very successful, okay? But in recent years, Intel basically what it did was, it provided the very same, we call the instruction set architecture, okay, but with a different implementation. But in the recent years, Intel got this to act together, and it's now leading semiconductor. AMD has fallen behind, okay? It doesn't, for example, produces its own processors, rather it uses some foundries, silicon foundries located, outside. And from Intel's point of view, it has a little bit of rough time when it was switching to 64-bit. Okay, so in 2001, Intel wanted to move from IA32. Remember, it tried to remain backward compatible to its previous previous processors. So then it says, I'm moving IA64 to IA64, so it's 32 to 64. It was a completely different architecture, okay, and used this IA32 code only as a legacy, but the performance was very disappointing, okay. And 2 years later, AMD came in, and instead of coming with a completely different architecture, they said they just, added some extra instructions, okay, okay, and they call this x86 64. Okay, now for basically officially it's called AMD 64, and Intel basically felt obligated to focus on this, but it was hard to admit the mistake. And then later, basically in 2004, a year later, EM basically did an extension to IA32, which essentially identical to what AMD had proposed. So it's a surprise. And nowadays, all but low-end x86 processors support all x86 64, but despite this fact, you'll note that a lot of code still runs in 32-bit mode, and we'll see basically the difference between 64 and 32 bits. So I can see a question here. Okay, what about power consumption of x86 versus ARM processor? Well, x86 is usually much power hungry. ARM is simple. We'll see basically why producing ARM processor is cheaper and hence it's more efficient. But Intel also has this Celeron line of processor which is designed for this, but you need to look at this. Okay. So our coverage within this course is that IA32 we will, in the past when like 10 years ago we were focusing on IA32, okay, which was the traditional x86. But now in this course we will be focusing on basically x86 64. Okay, this is the standard, and this is what's running on our machines. And in the book, we'll be covering 6884. But as a side note, we'll say here what was different in IA32.